And I also ask, we don't have Chibuke to our committee member, if they can contact him or not.
Okay, I thought I heard someone say that they were there. No, maybe not. Okay.
It's the time, but like I cannot see the name, but
No,
like I would double check with the company. Yep.
Okay, thanks. That would be great.
Yep.
Okay, I'll get started. So thanks everyone for coming to this general air quality session. So I don't want to waste any time. So Sean, if you can share your presentation. So our first presenter will be Sean Ford, looking at satellite-derived ammonia observations.
Okay, is that visible?
Yes, thanks. So sorry to interrupt, but I'll chime in at 10 minutes with like a sort of 2-minute warning for all the speakers. So if you hear that, if you can start to wrap up, that'd be great. All right, thanks.
Yeah, sounds good.
Ready.
Okay, sorry, I'm just setting up. Okay. Okay. All right, so hi everyone, my name is Sean Ford. I'm a co-op student from the University of British Columbia, currently working with Environment and Climate Change Canada. Today I will be presenting on satellite-derived ammonia observations and some of the improvements and applications we've done with them. So within this presentation, I will be discussing the background motivations for measuring ammonia, the background information on the satellite instrument we use to measure ammonia, the applications of the previous CRISP-Fast physical retrieval ammonia product, the limitations of that product and the update we've done to it, and the application of Noaa 20 data to that product. So why are we measuring ammonia? So ammonia has been recognized to have a significant negative impact on health and the environment in areas such as air, water, and soil quality. Ammonia emissions are also both currently increasing and expected to continue increasing in the future. So measuring ammonia is important for determining its impacts on humans and ecological systems. To measure ammonia, our group is primarily using the CRIS instrument, which has a few details I'll quickly go over. So it's a Fourier transform spectrometer that measures upwelling infrared radiation. It can be used to retrieve ammonia profiles of volume mixing ratios using a physically based optimal estimation retrieval. It has a 14-kilometer spatial pixel size with global coverage. CRIS is most sensitive to ammonia in the boundary layer and has excellent instrument noise. It's active on both the SNPP and Noaa 20 satellites since 2011 and 2017, respectively. And we have applied the CRISP-Fast physical retrieval algorithm to radiances from both instruments to compute ammonia concentrations globally from May 2012 to the present. So on this slide, we've used the CRISP-Fast physical retrieval product to create a single-day scene comprised of the CRIS surface ammonia pixel observations taken on August 12, 2017, combined with VIIRS true color images that were used for the cloud and smoke data. This particular day has examples of clouds, smoke, and non-signal pixels, kind of shown in Hudson Bay area. These non-signal pixels are the result of ammonia concentrations being below CRIS detection limit of 0.3 parts per billion. In the previous version of the CFPR product, these non-signal pixels are identified but skipped, and this can result in high biased gridded average values in regions where typical concentration values are low. So these non-signal pixels I've been mentioning are attributed to one of two causes. Either there's a thick cloud present, or it's what we call a non-detect, which is a pixel where the ammonia spectral signal is below the CRIS detection limit. To distinguish between clouds and non-detects, our group has developed a CRIS ammonia cloud detection algorithm. The algorithm uses the University of Wisconsin's CRIS image product that provides VIIRS cloud information matched up with the CRIS pixel, which our group combines with the additional functionality of identifying thick smoke plumes that VIIRS incorrectly identifies as cloud. For pixels that are identified as a non-detect, we assign them representative background surface concentration values based on in situ surface station data in non-source regions. With the usage of this algorithm, the newest version of the CFPR product now includes information on clouds and accounts for non-detects. So here we have a diagram to demonstrate the process that each CRIS pixel goes through to get assigned a cloud and non-detect flag. First, the pixel is checked to see if ammonia signal was detected, and if so, goes through our retrieval algorithm. After that, the pixels then get ran through the cloud detection algorithm, and depending on the results of that, can get assigned as clear, cloudy, smoky, non-detect, or if it's a thick cloud, it's just skipped. Non-detects, as mentioned before, are given the non-detect flag when there is no ammonia signal present and no clouds detected in the pixel. So the results of this algorithm are shown here using the same spatial and temporal range as the previous global plot. On the left is a plotting of the cloud and non-detect flag. On the right is the surface ammonia concentrations again, but this time including non-detects. You'll notice that over Hudson Bay, there's a few more pixels, and those are the non-detects. Non-detects are marked with purple, and we can see, yeah, like Hudson Bay is full of purple, along with some parts of Eastern North America and Northern latitudes, Canada. The cloud detection algorithm also shows you can identify smoke as these red pixels and as thin clouds as these yellow ones. The takeaway from this is that the inclusion of non-detects creates better representations of the background values and better statistics for gridded and average products. So here are some examples of those gridded and average plots. They all use the same data from May 2012 to May 2021 with a 0.1 by 0.1 degree grid. On the top left, you have the surface concentrations without non-detects. On the right, it's the same, but with non-detects. Bottom left is a relative difference plot where the data with non-detects is being subtracted by the data without non-detects. And finally, on the bottom right, we show the data density or the percentage of non-detects when gridded and averaged. From looking at these plots, we can see that as you go from without non-detects to with non-detects, the background regions have their surface concentration values reduced. So this is pretty apparent in areas like Russia or Canada. But for source regions, they are relatively unimpacted. You can see India, even with the change, it barely shows any difference. Yeah, and then from the bottom two plots, we can see that the regions with the highest relative difference are also the ones with the higher non-detect data percentages. So on this slide, we have the same spatial and temporal set as before, but this time expressed as box plots. The top is a relative difference plot, while the bottom is a data density plot. Starting from higher concentration bins, as you go to smaller and smaller concentrations, the significance of non-detects becomes apparent. The relative difference becomes more, it increases or decreases in this case, I guess. On the data density plot, same thing. As you go from higher concentrations to lower concentrations, the percentage of non-detect data, it goes up significantly. On this slide, we compare the biweekly averages of CRIS data to AMON surface observations or in situ data, where we've shown 4 American background surface stations. The red bars are the CRIS data without non-detects. The blue bars are the CRIS data with non-detects, and the black bar is the AMON data, the in situ data. The main thing we notice is that for all of the data in this slide, the distribution of ammonia concentrations for CRIS get closer to the in situ data when we add non-detects. So from red to blue, it gets closer to the black coloring. So the majority of this presentation was focused on the addition of non-detects, but we also wanted to share some information about the addition of Noaa 20 data to the CFPR product. On the left, we have a daily and an annual 2020 S&P plots. And on the right, we have the same, but with Noaa 20. Overall, the observations are very comparable. There are some slight differences due to the different observation times. But it's pretty minimal. There's a mean difference of negative 0.05 parts per billion, or in relative terms, negative 3%. The preliminary results look pretty promising, and we hope to use Noaa 20 to continue where the S&P data set left off in May 2021, and to create a multi-decadal ammonia data set using consecutively launched CRISP instruments. So to summarize what I've been talking about, the new CFPR ammonia retrieval product adds in cloud information and identifies and accounts for non-detects. Adding non-detects to the CFPR product produces high bias statistics in non-continuous source regions. In these non-continuous source regions, there can be a significant amount of non-detects, reducing average background values relatively significantly. Source region gridded values are mostly unaffected by the addition of non-detect data and have low non-detect data density. And preliminary CRISP-1 and CRISP-2 comparison results during the overlap time period suggest that the two instruments can be used to produce a multi-decadal ammonia dataset. The SNPP results are made publicly available by Environment and Climate Change Canada. So that's the end of my presentation. I'd be happy to take questions now if there are any.
Thanks, Sean. So I guess for questions, if you want to raise a hand, or you can probably jump right in, really.
Yeah, I'm trying to see if I can see the chat, but I might have to stop sharing if I want to do that.
I can see hands on the participants, and yeah, I can nothing in the chat at the moment that I can see.
Okay, well, if the person who has their hands up wants to ask, I'd be happy to try to answer.
Perhaps I could start with a question. I know it's a bit outside of how the instrument works, but I'm just kind of curious. Do you know much about the vertical profile, what that would look like, and how that might affect the interpretation of your measurements?
Well, we did do, because a lot of the content on this presentation was based on an upcoming paper we're doing. So we did make total column plots, and they looked pretty, yeah, the significance was, or it was impacted by the addition of non-detects. I don't have them available with me right now, but I'd be happy to email them if you are interested in those.
Okay, I'm just curious, is in general, most of the concentration, do you expect to be sort of near the surface or elevated?
Yeah, I mean, yeah. So like I said, CRISP is most sensitive to ammonia in the surface layer. It doesn't stay in the air for too long. Yeah. So yeah, most of the significance will likely be in the surface.
Okay, thanks. That makes sense. Colin, what question?
Thanks, John. That was really interesting. I think I missed how exactly you're using the non-detect data to decrease these background values. I didn't quite catch how that works mathematically.
So when CRISP has a pixel that doesn't like when there's no ammonia signal detected in a CRISP pixel, it's either a thick cloud or a non-detect, as I mentioned. The non-detect values are very low. If they're below the CRISP detection limit, we can assume that they're quite low ammonia values. So we used in situ surface data to create representative values. I think I actually have a slide here.
I see. Okay.
So these are the representative values that are chosen based on the temperature of the CRISP pixel, as temperature is highly correlated with the ammonia. And we use these values in place of a lack of signal.
Okay, I get it. Thank you. That's very helpful. Yeah. Thanks.
Mm-hmm.
Good preparation of a extra slide.
Yeah, I figured that might be a question.
Time for another. There is. Okay, well, thanks, first speaker. That's great.
Thank you.
Is Chibuke here under possibly a different name, or?
I don't think so. There's still 1 minute left, but I didn't hear anything from the committee as well. And what I heard is we may wait for him, but I think it's up to you. Like, if he's not showing up like in a minute or two, then maybe it's your decision.
I'm inclined to keep the schedule and wait, especially on Zoom, because it allows people to take a little break.
Yeah, we still have 1 minute left.
Yeah, so let's hope we get the last minute arrival.
Yeah, but I don't think they contact that person separately or so. I think they're quite busy to handle.
Okay.
And
if anyone here does know any contact and can reach out to Cfpr, that would be great. I don't have any.
I think he's somewhere, or she's somewhere in BC, but other than that, it's hard to guess based on that.
UNBC, I think is the. Okay, so yeah, sorry for the gap, but I think it'd be best to try to keep to the schedule. So in case anyone's showing up according to the posted schedule for a specific talk. So if we do get an arrival, we'll have a really quick condensed talk, but otherwise we'll just have a gap. And of course, if anyone wants to fill that gap with any initiated discussion, that's fine too. But otherwise, we'll just take a break and wait till 10:25. So again, sorry about that.
Actually, I had a little question, kind of amateur question naive question to Sean. And
please.
Does the satellite have a capacity to measure ammonia in the wintertime as well?
Yeah, it can do any time, any spatial range.
Yeah, one thing I asked to Mark, and he said maybe you need to have some clear temperature contrast between atmosphere and Earth's surface to measure ammonia ambiguously. But that condition is not really met in the wintertime. So that's why he wasn't so sure about the possibility of measuring ammonia from satellite in the wintertime. And what do you think of that?
I don't want to missay anything because admittedly his knowledge on the subject is far stronger than mine. But when I've been talking with him, he didn't seem to think there was any problems with measuring in the winter. Maybe the values are better in the other seasons, but yeah, so far we've been able to do any season, even winter.
Okay. Yeah, sometimes you see very high ammonia concentration near the farm, maybe even in the winter. And I wonder if that's detectable from the satellite.
I do know that, in the winter, because there's less of a growing season, we do have a lot more non-detects available. So I guess that's a little different than your question, but so far it seems like winter is totally fine for Chris.
Okay, interesting.
Yeah, I know someone was asking about total vertical columns, right? Because I looked over my paper in this a little break, and I have total column plots if people were interested in that. But yeah, if no one's interested, that's fine too.
You should show them. They always look really nice.
Okay, sure, I'll show them.
Please.
So yeah, this is on the paper draft we're doing, and this is just the total column plots. So I mean, you can see there's definitely a difference there, going from a lot of parts that are like near 1.2 to going down to I want to say 0.4. And then you can see with the difference plots that it's probably around 50% relative difference, minus 50.
And so how are you using the non-detects for the total column? Because you said you were using surface monitoring data to help you fill in the gaps.
Well, Chris Monitor, it does the, we picked values based off of in situ data, and then we apply it whenever we don't have a pixel below, when we have a pixel below the detection limit. So it gets added to the total column, but the other columns, I have to,
So you're assuming a profile or something?
Yeah, I'm sure there's some internal calculations I'm not quite aware of, but yeah, it gets, the non-detects do get applied to the total column. I don't know the actual internals of it.
Sure, okay, that's fair. Interesting.
So thanks for keeping the discussion going. So I'll just take a 10-minute break, and if everyone can rejoin or repay attention at just before 10:25, that would be great. And Kenjiro, you're welcome to set up the share anytime you like.
All right.
Thanks. Okay, so thanks to everyone for hanging in there during that little break. So we will continue. Our next speaker, Kenjiro Toyota, will talk to us about 3D regional model simulation of dry and wet deposition fluxes, inorganic mercury species in the springtime Arctic. So anytime you're ready.
Okay. Hello again, everyone. My name is Kenjiro Toyota from Environment Canada Air Quality Research Division. I'm going to talk about the regional model simulation of mercury chemistry in the Arctic boundary layer and the deposition into the surface. And this work has been collaborated with a lot of people from the GenMark model developers, and I used a lot of field data obtained in situ on the ground from including over sea ice for mercury, ozone, and sometimes max DOAS BRO measurements, even on sea ice. And I used the satellite BRO data and the snow melt date retrieval, and sometimes wet deposition. Not all the data I can present today. So anyway, so why mercury is important in the Arctic? It has a toxic effect on animals and humans, mainly in the neurological aspects. So reproduction and hunting ability and those kind of things can be influenced by the high level of mercury in the body. And that's caused by the mercury deposition from the atmosphere. And in the Arctic is kind of peculiar because you have a lot of river inflow that can also bring major amount of mercury into the Arctic Ocean. But still, maybe atmospheric deposition is slightly more important than riverine discharge. And this atmospheric deposition is believed to occur mainly in the spring when the bromine chemistry is very active over sea ice. However, it is very difficult to simulate in the model. And so far, all the mercury models have used the highly parameterized bromine chemistry in the boundary layer, like BRO concentration given by a function of temperature, which is maybe okay or not okay. We still don't know. And so this study is aims at simulating this chemistry associated with bromine over sea ice in a more explicit manner. Although the source term for bromine is still empirical, but we do simulate the chemical reaction in an explicit fashion. So here's the approach we're using. GenMark is a Canadian operational air quality model, which of course doesn't simulate bromine normally. And also Arctic region is not really a region of interest. So what we do here is the extension of the chemical mechanism into bromine and mercury, 7 species for bromine, 3 species for mercury. And we also included the air-snow mass exchange for bromine and mercury. And some technical details include the subfriction velocity and Obkoff length for the calculation of dry deposition velocity is given for the 4 surface types assumed by the GEM weather forecast model, soil glaciers and water and sea ice. That is actually important because if in between sea ice, you sometimes have open water leads where you have a very high sensible heat flux so that the air is almost always unstable, whereas over sea ice, it's almost always stable. So that contrast can be represented by this approach. And also we have taken into account the in-cloud scavenging efficiency reduced within the mixed phase clouds, where the evaporation of liquid cloud droplets occurs for the growth of the ice particles, so that the soluble tracers and the hygroscopic aerosols, once contained in the liquid water part of the mixed phase clouds, cannot really make it to the ground by the wet deposition. That effect is also taken into account. And as I show in this diagram in the upper part, bromine chemistry is kind of simulated in a quite explicit manner for the 7 inorganic bromine species within gas phase and the aerosol surface, and the deposition of ozone, HOBr, and bromine nitrate are assumed to produce Br2 over the sea ice and especially snow containing trace amount of bromide, and it can give rise to Br2 back into the atmosphere. That's a very empirical function, so we need to tune up some of the parameters related to this process. And also mercury, bromine is actually main oxidizer in the boundary layer in the springtime, but in the summertime, OH takes over the oxidizer for the mercury. And after mercury is oxidized into divalent form, it can partition between gas phase and aerosol particle depending on the PM concentration and the temperature. And after deposited into the snow, it can be deduced back to the elemental form mainly by sunlight, action of the sunlight, so that this Hg0 elemental mercury is volatile and they go back to the air. That's again a very empirical parameterization. We are actually tuning up this parameter to give some reasonable results in the model. But again, this process occurring in the atmosphere chemistry is kind of explicit in our model. And this is one exemplary case in March 29th in 2012 around the Beaufort Sea and the Eastern Arctic Ocean region when there was a very intense cyclone developing over Beaufort Sea, which actually drew a lot of ozone-rich air into the Arctic Ocean from Alaska. And there is also other region where you see a very high BRO. That's actually the region where the ozone was carried from the Barents Sea very rapidly. So these two areas have a very, very high BRO concentration because the BR2 source term over the sea ice is associated with the levels of oxidants in the surface air. So this high level of BRO, and actually its BR atoms, can oxidize mercury very rapidly. It can end up in the wet or dry deposition, depending on the availability of the precipitation, mainly snow in this time of the year in the Arctic. And when the precipitation is low or temperature is too low, then dry deposition is a main cause of the deposition in the model. And this is a model evaluation example over OV4 floating over north of the Greenland at this time of the year in 2012, from mid-April to mid-June. And actually the buoy itself was launched in the previous year in the fall, and they ended the operation in the next summer. So it actually drifted away from the near the North Pole to the east of the Greenland over a year. And what I'm showing here is the results between the mid-April to the mid-June, when the buoy encountered basically the 5 major events of enhanced BRO column densities, which was shown in the pink. And the BRO was retrieved for the 2 type of quantities for the column density below 4 kilometer and below 200 meter. So both of these are generally well captured in the model when the cyclone approached to the buoys when you have very high wind, and that indicates the approach of the cyclones. So among the 5 events, actually four events associated with the approach of the cyclones was reasonably captured by the model. One event which occurred in the mid-May, indicated by this orange arrow, showing the very high concentration column abundance of BRO occurred, wasn't really captured in the model. That indicates that our simple tuned up parameterization didn't work well for this cold weather condition. Something is additional should be working, which we don't know yet. And also we have some evidence that during this occasion, the boundary layer development in the model was not quite sufficient based on the comparison with radiation data at ALAT. So basically the boundary layer in the model was too shallow during this case. So maybe both chemical or source term parameterization and the meteorology representation in the model were wrong in this case. So this map shows one of those cyclone related events on May 9th. So you see this, high BRO column abundance around the cyclones near the North Pole. And that was actually captured in the satellite, from the satellite to some extent. And also these two buoys were captured, these variations in the region, and also alert station also saw relatively high BRO column abundance. On this same date, actually there was snow samples for the total mercury in the snowfall alert, measuring the 11 picogram per gram, which is relatively high. And the model simulated the daily mean snowfall mercury concentration at 70 picogram per gram, which is actually higher, 7 times or 6 times higher, and which I think is a reasonable success. And at the end of the May, actually, OV encountered 0 degrees Celsius, which could have facilitated the snow melt. And after which point, there were barely no enhanced BRO column abundance, even when cyclone approach. That means snow melt could have washed away any bromide remaining on the snow on sea ice. And no matter whether disturbances arrive, you cannot really get high bromine concentration anymore in June. That was captured by the way we parameterize the snow source time by assuming the snow BR2 source can happen when the instantaneous surface temperature is lower than -1 degree Celsius and snow depth is greater than 5 centimeters. And we also assume that the exposure to surface air temperature greater than 0 degree can deactivate the ability to for the BR2 release from the sea ice for the rest of the season. The limitation here is that we don't account for the drift of sea ice with time. So that's one limitation of the parameterization we use. And here's a time series for the surface ozone and mercury, gaseous mercury concentration at 3 sites at Barrow, which is currently called Utqiagvik Peak, and also Alert and Nielsen. And as you can see, blue is our model results and red is observation. And the correlation coefficient between these two terms at hourly concentrations are about 0.6, so which is, I think, very great. And these depletion events basically occurs from the beginning of March and to the end of May at all stations, and these beginning and terminations are generally well captured, although we saw some false depletion events occurred at the end of May at the alert. That indicates some weakness in the model parameterization for the source term at the relatively high temperature. So again, looking at this result in a different way. So this is a density plot for the correlation between ozone and the gaseous mercury concentration at the Nielsen at the lab. Upper panel shows the observational data and the lower panel shows the model results. And this indicates the nature is more complex than the model because the model correlation is too tight. We are missing the mercury emission from the sea surface, which can occur from the open seawater. That's neglected in the model. That's one source of this scatter in the observational data. And we also ignore the bromine chemistry associated with the sea sprays over open water. That's also relevant probably at Nielsen, which is close to the open ocean. And as I told just now, the weakness in the model is the bromine source term at the relatively high temperature, perhaps above -10 degrees Celsius. Under some circumstances, bromine can be released very significantly, but at other times it's not. So that kind of separation is not really captured yet. So that's one weakness. So this slide shows a lot of information. So I just want you to concentrate on the plot B time series. That shows the snow concentration of the snowfall and ground snow concentration of the mercury There are about 12 samples for the snowfall and 3 samples for the ground snow. And these squares represent the ground snow concentration, so which drops from 37.5 to 3.2 in late May. And that point, actually, we are still simulating some mercury depression events, which observation doesn't really see. But the one snowfall event, which was sampled on May 23rd, indicates a very high concentration of mercury in the observation, and that was actually reasonably captured in the model as well. But because we are actually still depositing mercury at this time, after this point, whereas maybe in the reality, mercury is not depositing anymore, so we are actually delaying the timing of the concentration of mercury in the ground snow at the end of May when the snow melt occurs. So looking at the whole Arctic Circle domain of the model, this model obtains the net deposition of mercury in the marine part of the Arctic Circle, received the mercury over the 7 months from February to August at the 78 megagram, whereas over the terrestrial domain, it received mercury at the 59 megagram. Overland, 61% of this deposition is due to the dry deposition of long-lived elemental mercury, which is occurring mainly in the summer. So the springtime bromine chemistry is not making a major impact on the mercury deposition over land part, terrestrial part of the Arctic Circle, whereas over the ocean, this is mainly caused by the springtime bromine chemistry. Gross deposition over the 7 months period is 136 megagram, which is occurred by the dry deposition of gaseous oxidized mercury and wet deposition of the particulate oxidized mercury. And 79% of this deposited mercury is once trapped in the snowpack. And at the end, slightly more than half of it is emitted back to the atmosphere by photoreduction to the elemental mercury, and slightly less than half can eventually enter the seawater when the snow melt occurs mainly in the June. That's just the model simulation indicates. So to summarize, we have developed the extended version of GenMark with the bromine and mercury chemistry, which can simulate the bromine chemistry in a very explicit manner, even though the source term for bromine is still empirical, which has not, this sort of explicit representation of the bromine chemistry has not been really conducted for, at least for the mercury modeling in the Arctic. And this model has a good capability in simulating the enhanced bromine chemistry under the synoptic weather disturbances such as cyclones, whereas the model is not so good at capturing the enhanced bromine chemistry, sometimes occurring under the calm weather conditions as well. And so that's maybe the cause of this problem is associated with the lack of the consideration for the NOx chemistry, which can actually recover the ozone concentration after ozone is destroyed totally. That aspect is actually totally ignored right now in our parameterization. And also we have some evidence that the growth of well-mixed planetary boundary layer is not always captured well under the fair weather conditions. That's a kind of a weather forecast side of the problem. And we have some doubts that sometimes open lease presence is not really captured in the ice analysis as well. That may also cause a problem in the model meteorology, especially in the boundary layer mixing. And on the side of our own problem, we have a clear weakness in the parameterization of the snowpack bromine source term at temperature at close to the melting point, like about the -10 degrees Celsius. And that's when the mercury can also flushed away into the aquatic biosphere. So that's a very important part of the parameterization we need to improve in the future. So within the Arctic Circle, net deposition of mercury is simulated to occur at the 78 megagram over the 7 months period over the ocean. And that mainly occurs in the springtime from March to May. But most of these deposition is once trapped in the snowpack, and final entry to the marine aquatic system is maximizing in June when the snowmelt occurs across the wide region of the Arctic. And our estimate, the 78 megagram over the 7 months is within the previous estimate between 45 and 108 per year, which has been previously estimated by the empirical parameterization of bromine chemistry. So that's it from me. Thank you.
Thanks. That's great. Open it up to questions. I could start with one just as a general question. For simpler chemical species deposition, you can represent just as a deposition velocity that you can multiply by the concentration. I wonder, like, you know, clearly this is much more complicated than that, but is there a comparable deposition velocity that you would get for mercury, and how would that compare to other chemicals? Just for dry deposition.
Yeah, that's a good question. Actually, there is a big uncertainty for especially for the oxidized mercury over the snow, and it's obviously very rapid, and maybe it's like SO2 or nitric acid. And the parameterization we use actually assume the very small surface resistance. So it's actually even smaller than SO2 under the freezing condition. SO2 assumes the relatively high surface resistance at a very low temperature. Like its dry deposition maximizes at around the melting point. And then if you freeze down further, you get relatively smaller dry deposition velocity for SO2. And nitric acid is normally assumed in a different way. It is assumed to deposit very rapidly down to the very low temperature. And what we assume for the gaseous oxidized mercury dry deposition is similar to nitric acid, so that it can still deposit very rapidly under the very cold conditions. That's actually one uncertainty, but there is only one field measurements claim that, you know, tendency before, and we don't have any more than that.
Yeah, that's a difficulty.
Yeah, the interesting thing is that even though we assume the very rapid dry deposition under the very low temperature, in the cloud side, we assume that the ice clouds are not so effective in, you know, taking up the gaseous oxidized mercury. That's probably one sort of, you know, contradictory assumption between the two. So, yeah, but we don't know.
Mm-hmm. Okay. Time for another question. Okay, well, I'll leave it open because we'll wait another couple minutes to start the next session anyway. So if anyone thinks of one, or if you'd like to just enter it in the chat, if that's easier, that's fine. I could ask, are there more? Is the measurement campaign sort of continuing to provide data to run into the model?
Sorry, what did you say?
I was just curious if the measurements are continuing sort of to come in, or was it a?
I don't know. Yeah, these ovoids are very unique and useful for the validation of this type of model. I'm not so sure they are still continuing this activity anymore. They don't really update the data after 2016 or so. So I don't know if they have carried on after that. it's obviously supported by NSF. Yeah, so VRO has been measured, very actively up until some point, and people are kind of going away to something else right now.
Okay.
Yeah, that's unfortunate, but I don't know.
Yeah, but lots of work.
There are more interesting stuff at other science.
Fair enough. Okay, so we should continue. So thanks again, Kentaro. That's really interesting. So our next speaker, Andrew Kovacic.
Yeah, Kovacic.
Kovacic, sorry about that. So if you want to share your screen.
Let me do that.
And Andrew will be presenting satellite monitoring for temperature-based prediction of springtime pneumonia and agricultural practices. So moving a little south. So anytime you're ready.
All right. So hello there, everyone. I'm Andrew, and today I wanted to share some of the a nice little tool that we've completed in the last few months. At ECCC, we have a lot of needs for predictions as to when to release ammonia emissions in our models. And today I want to share one that's really quite simple. It's a temperature-based prediction model, but I think you might agree that in its simplicity, it can gain a lot of use. So to begin, I first want to go back to a previous model that we were working on. And in this model, we were basing it off of farming practices. So for instance, in the Netherlands, which is what this plot is showing, they have very strict regulations on when farmers are allowed to plant crops, when they're allowed to spread manure for all different kinds of plants. And from this, we went and we grabbed those regulations, and we, using a couple models, we put all that data in, and just using time and that information, we were able to get very good predictions on these ammonia emissions. So for instance, in this plot here, these blue data points are a ground-based station in the Netherlands. These colorful points are satellite measured data from the CRIS satellite that Sean talked about earlier. And in orange here, you can see this is what we predict just from these farming practice regulations. And so this actually fits very well, I would say, as far as what we're concerned with, which is getting the peak, getting the rough amplitude, getting the time to trigger this pretty well. We were quite happy with this for those reasons. However, there were a couple downsides to this, which the first is it's really hard to find these regulations. You go on government websites and you go through links and links and links, and you hope you find what you're looking for. Sometimes you don't. Some countries just don't even have these regulations. As well, governments change, rules change, and if these regulations change, you might not have a good way of knowing that. So this was nice, but we kind of wanted to think of maybe a simpler model that we could get similar results for these predictions. So from that, we came up with the following prediction hypothesis statement. That being that regardless of these regulations that are in place, the farmers are under an economical pressure to plant their crops and spread the fertilizer as soon as possible so that they can harvest the crop and use the land further. So regardless of any government rules, they're still under this pressure to plant as soon as possible, whether that's the government or whether that's temperature. So in regions where there are strong regulations, then we expect that the date that they're allowed to spread fertilizer, for instance, should correlate well with like an average temperature, for instance. And in regions where there's weak or little regulations, there should be a very strong correlation with temperature trends, because farmers are smart. They know when it's safe to plant crops, when it's safe to spread fertilizer. And so we should be able to see that in the temperature data with when they're spreading. As well, to avoid early triggering and say like a warm week in the winter, we want to use temperature summed values. So for any date, we're looking at the temperature that constitutes all the days up to that point in the year. As well, the temperature summed value has a nice benefit that you get linear growth once you kind of reach your maximum temperature for the year. Whereas if you take average temperatures, as you get to that max temperature, your average temperature kind of asymptotes towards that. So what we have here on the left side here is a couple plots. So on this top plot, we have, I think it's either 4 or 5 years of ammonia concentrations in America overlaid in their temporal space. So we have 4 years of data and their emissions for this region. And what you see is there's definitely some kind of triggering point that happens after March, but it gets very jumbled in the temporal space. It's not clear if you wanted to just fit a Gaussian into this, where would you fit this? You know, some years it looks like it's like March 10th, some years it looks like it's more March 4th. So it's not clear. However, if for each of these days we assign this temperature summed value and we plot instead the temperature sum values versus their emissions, we actually get a very clear triggering point that it seems to be at the temperature sum being above 0 degrees. So what we do then is we take that temperature summed value for that specific region, and over the many years we do some binning and we get a pretty clear triggering point. We can then fit a Gaussian through it, and then we take that Gaussian and we apply it to years that we didn't include in our analysis. And although the timing isn't perfect, you can see it looks here that when we look back in the temporal space, we're a little early for the very limited information it took to give this model. We're pretty satisfied with how well this works. It's not much more than any temperature data required, and a lot of history of data that we happen to have. Here is the same analysis from that previous slide. However, I've unincluded different years so we can analyze those years. And you see for all of them, it seems to get the triggering point quite well. It hits the peak. Sometimes the amplitude's a little off, sometimes it's a little wide. But again, the main thing we want to be able to get is that first peak and when these emissions should start to get released, which it seems to do quite well. Here I wanted to highlight in some regions for different years, it doesn't work perfectly. And this is one example where maybe I'm not so satisfied with this. It looks like in the actual data here, there is some peak that's happening. This looks like maybe February like 25th. It looks like there's some peak there, but our model seems to overestimate this peak. We're playing with a couple different adjustments to this to maybe be able to get rid of issues like this. And then I just wanted to highlight a couple of points that we're kind of finishing off to look into this to improve a little. So firstly, the model uses this temperature sum value that I mentioned, but we kind of just took the very straightforward method at first, which is to just go back for the whole year for each temperature value. And you know, for most regions, this really has no issues. A couple years, though, you'll get issues for the reasons that, you know, if you're taking the temperature sum for the whole value, if you have a huge outlier winter, you might throw your temperature sum off by like 100 degrees Celsius into the negative. And so then even if you have a regular spring and things are progressing as they should, your emissions are delayed a little bit. So the obvious solution that we're playing around with is how far back should your temperature sum go? It seems like it's probably going to be around the previous month, maybe month and a half, 2 months, something in this range. Then you're getting the data which is relevant to you. Like if you had a lot of cold days in the last month, you're probably still going to have frost or permafrost in the ground. If you had a lot of very hot days, that might help defrost the ground. Secondly, you know, we're physicists here, and you know, we see a curve and we hit it with a hammer of a Gaussian. That seems to work pretty well, but if I go back a couple slides, you might notice it has this tendency to almost, when it's doing this fitting, it kind of almost is making like a step function. So it might just happen to be that a step function or some other curve is more optimal for this. For now, we're just using a Gaussian. Lastly, we've tested this model in Europe and the North Americas, which are all rather far from the equator. And they then have this very distinct springtime temperature change that is really what's kind of driving this model, because we're assuming that the farmers are acting optimally with this temperature change. We're wanting to see how far we can push this. So as you get closer to regions where it's more of an annual temperature, this is going to start to fail, and we're wanting to see how far can these regions get before it really does fail. And I think I'll end there. I hope I got some key points and maybe got a bit of interest there. And thank you for your time.
Thanks, Andrew. It's very interesting. So I'll open it up to questions. Feel free to use the chat as well. I'll ask a really general question. I'm not like a big proponent of machine learning or AI, but this would seem like a pretty good application. Or is there an importance in sort of knowing the physical reasons?
I think that's an awesome question. I've kind of played with this idea a lot. I just have absolutely no background in machine learning. Perhaps this is something that might be good, like a future co-op student, someone like fresh out of university, maybe has that computer science background. That might be something they could really dig into. I think it definitely has some very strong applications. A lot of these trends, I think, are things that you maybe only understand after you've seen the data shown in a specific way. So maybe this isn't a very sciencey thing, but if you have this machine that's giving you good fits and good models, maybe then after you see that, you could go, oh, okay, maybe here's the physical intuition for why that's happening. Mm-hmm. Maybe not the best scientific method, but I think there's some utility there.
I mean, in some respects, you're mapping human behavior, so there might not actually be physical reasons.
Yeah.
When farmers feel like doing it. Yeah. But hopefully there is a logic to it. We got a few minutes.
Did you look at any other variables or just temperature?
It's kind of been like a continuous stripping down of other variables, actually. A lot of, I guess I should say, there's a lot of different kinds of ways you could measure the temperature. There's like soil temperature, the atmospheric temperature. We've played around with those. Really, the main thing we started from was the crop-based data when they were allowed to spread. And then from that, we that's how we actually got into this temperature sum, is you would get the crop data and that would work well. But then we found if you took this historical data based on when they were allowed to spread fertilizer, and then you took the temperature sum for that date, you would get a very good fit. And then we kind of realized, like, you don't even really need this fertilizer data if you just take this temperature sum and fit it out right.
Interesting. Okay.
Yep. I think there's some way to adding or subtracting some of variables if you are using really machine learning stuff. There's a whole bunch of ways to make it easy, but I think there's some drawbacks. It doesn't have any physical meaning, as Mark said. So if your data is biased a little bit, the machine learning algorithm cannot do better than that. And also there's some drawbacks of overfitting. So sometimes it's doing well for some of variables, but if you start to bring it something else, then it start to losing some of benefits. So, for me, I had hard time to persuade those reviewers to say this machine learning method is applicable, and they ask why no one tried this before, and all of a sudden you are trying to do this from computer science. So that part make a bit hard for you to make sure for that.
That's really interesting. What kind of data were you fitting with machine learning?
Mine was radar data, and to make a decision. But I think we can talk a little bit more. It's the time for Victoria now. Thanks.
Yes. I'll stop my screen share and all.
Thanks. That's interesting. And then Victoria. So next speaker is Victoria Pinnagar. Looking at cloud-based height correlation between a co-located micropulse LiDAR and I'll just say lift ceilometer. Skip the digits. Anytime you're ready.
Okay.
Starting, it seems to be a bit of a lag. There we go. And then if you switch to presentation, perfect.
Yeah. All right. So if everything's good, my name is obviously Victoria Pinnagar, and I am a student working with Dr. Robert Sika at the University of Western Ontario. So I work to help him establish and utilize the new MPL or micropulse LiDAR network called MPL-CAN. So one of the sites of which is here in London, and it operates our co-located MPL and ceilometer. So to start off, what is MPL-CAN? So MPL-CAN is a network of micropulse LiDARs, which I'll explain what those are in a little bit, across southeastern Canada, currently with an additional Arctic site in Eureka, which eventually will have several other sites, but those are the current ones that we operate. Most of these sites have been coming online over the last 2 years, with the longest running site being Sherbrooke, Quebec, which has operated since September 2020. And our London site here has operated since December of 2020. So all of these sites, we at least have what is called like a mini micropulse LiDAR, as well as a smell stun photometer and a purple air quality sensor, which uses PM 2.5 and the PM 10 air quality sensors. So the goal of our network is to hopefully develop a cross-country smoke tracking and particulate tracking for with forest fire and air quality management, as well as hopefully like improving aerosol characterization and modeling across the country. So we operate in partnership with both NASA's MPLNet and then the European Meteorological Network's eProfile network. So NASA's MPLNet is quite similar to MPL-CAN, obviously, where it's a micropulse LiDAR network that utilizes CMOS as well. And they distribute data products across for public access, including normalized relative backscatter, volume depolarization, cloud-based, and other such. And they also have 24/7 access to all of their instruments, and all of our MPL data is hosted on their network. And then additionally with eProfile, our ceilometer that operates here in London is a part of this observing network of various remote sensing instruments that include automated LiDARs for wind and particulate tracking. And we are one of, I think, the only North American partner with an instrument in this, while most of the other instruments operate in Europe. So here in London, we operate our ceilometer, or CHM15K. It's also, I think I continue to reference it as the Luft ceilometer. And then we also have our mini micropulse LiDAR. So the biggest differences between these two instruments are their wavelength, which the Luft ceilometer operates at 164 nanometers and is just a basic elastic backscatter LiDAR. And our MPL, or mini micropulse LiDAR, operates at 532 nanometers and is a polarization LiDAR. And so both of these produce a cloud-based detection, which in all hopes would obviously give you the base of what you'd assume is a cloud with little to no pulse detection. But due to some instrument differences and obviously some algorithmic differences, this isn't always the case. So one of the biggest differences that I just mentioned about the difference between the MPL and the ceilometer is that the MPL is a volume or a depolarization or polarization LiDAR. So they produce a volume depolarization ratio due to the LiDAR having dual channels of polarization at about 45 degrees, which allow us to accurately view structures for the atmosphere, for the differentiation between maybe high scattering aerosols and clouds, such as ice clouds. So as you can see here on the left, this is the normalized backscatter for both the instruments. So the ceilometer on the top and the MPL on the bottom. And when viewing, you can obviously view like very high scattering clouds and the less aerosols. But one of the biggest things when you observe this in the depolarization ratio is the ability to actually accurately view the ice populations. And then also you can very clearly see large plumes of aerosol coming in. So for example, between noon and 6 o'clock here on the volume depolarization, you can see in the red is a very high ice cloud, which underneath is actually a aerosol plume, which as you go on farther into the day, you can see a very, very high scattering aerosol, which has the potential to be misidentified as a ice cloud, which hopefully can be mitigated by utilizing sort of both these instruments. So because we wanted to view the possibility of issues between these instruments, we used the MPLNet product for the cloud-based height and the Luft product for the cloud-based height. And we just did a simple regression. So because we want to use these for climatological surveys, we wanted to know whether or not these instruments represented a congruent measurement. So we don't lose or misidentify cloud layers as aerosols or misidentify aerosols as cloud layers. So the first thing that was noticed when we looked at the total cloud coverage over spring of 2021 was that the MPL saw less total cloud coverage than the ceilometer, which most of this discrepancy comes in between 0 to 2 kilometers, which obviously has issues with the planetary boundary layer and all of these mixing layers. So between these heights, it's also very, very possible that the difference in observation may be biased due to calibration called overlap, so which is caused by the overlap between the receiver and transmitter at low altitudes. But the overlaps are individual to their instrument, and so we wanted to sort of eliminate this as the only reason. So utilizing the Luft and ceilometer products, Luft ceilometer and the MPLNet product, we looked at a one-to-one comparison of each of their simultaneous detections for the first layer, and the observation of the total of the vertical populations above the regression line should be relatively consistent if it were to be just a simultaneous, a bias due to overlap. But because during the winter months of this 2021 to 2022 run, when aerosol levels are much lower, the populations above the regression line are minimized in comparison to the spring, autumn, which is represented here as equinox, and the summer. So we want to go about identifying these as whether or not the salometer is misidentifying aerosols as low-lying clouds, or if we're viewing the MPL as misidentifying low-lying, lower scattering cloud as an aerosol. So we wanted to sort of go back and look at this by applying the same algorithm to both the instrument data sets. So to start off, what our goal is we want to reduce that high altitude population to make sure that instead of it, there's a simultaneous like low and high first layer. We want to reduce those and sort of bring it back towards the regression. So I wrote a simple cloud-based detection that utilizes what the MPLNet version 2 algorithm is as a frame of reference. So it's important to note that MPLNet currently uses a version 3, which is built for the addition of a more accurate high cloud reporting, but this shouldn't have an effect on the low layer, first layer detection, which is what we're dealing with. So the basis of the gradient base is we're taking the normalized backscatter ratio, and we're taking the derivative of this. And so everywhere that the derivative is above 0, we're trying to see an increase over a minimum of 60 meters to indicate a minimum physical depth of the cloud, as well as it passing a threshold value for the backscatter. So by applying this to our MPL data set to check if it was relatively accurate to what the version 3 was producing, we looked at the MPLNet on the Y and the gradient based on the X to see if we had reduced the populations above that regression line. So we have minimally reduced it, but obviously there are still some populations that are different between these two, which may indicate that our gradient based is more similar to what the left product would be indicating. While in the winter, when there's obviously less aerosol, it may be a worse detection. So when applying the gradient based to the MPL data and then comparing it to the left data, we actually have like a very minimal increase in our values, our statistical relevance, but as well as minimization of that population. So we're hoping that this can be used in summary as a bridge to help sort of when doing climatological surveys to eliminate what is a high possibility of having it be an aerosol. And so because the initial comparison between the two networks is overall quite high, it's just bridging that gap between that total cloud coverage and the low level cloud coverage. Utilizing this will hopefully better the ability to differentiate those misidentifications. And the code will be hopefully made public on GitHub for public use, which can be applied to any of the instruments in the network, as well as with very little change, most LiDAR using .mc. So if you have any questions, feel free.
Thanks. Okay, I'll open it up to questions.
Oh, can I have a quick question?
Yeah.
I'm not sure, but like, I'm wondering if there's any specific purpose of the new method or something. Like, you want to get rid of those outlier more, or you're focusing more to lower altitude or higher altitude or something like that? Because some may have different purposes of doing so. So like your purpose is like minimizing overall differences, or you have any specific target?
So our general goal is to minimize those misidentifications of what we assume are aerosols. So something that's not shown here, but one of the things that MPL-NET does is they produce an aerosol mask based off of their polarization and as well as the co-located smell. And when we utilize that product with our solometer, we do notice that some of the solometer data is misidentified in what the MPL-NET, utilizing like these other instruments' abilities, are aerosol masks. So hopefully, currently what my code is trying to bridge is to bridge sort of that aerosol misidentification without the necessity of utilizing the smell product. And hopefully after running it on more data that as we run them together, it'll get more accurate so that when it's applied to another instrument, utilizing sort of their individual instrument calibrations, obviously, then it will show sort of a similar trend and be able to help in that as well.
Thanks.
Yeah.
I was wondering, for my own benefit, since I'm not hugely familiar with LiDAR and reading the plots, if you could go back to slide 5, if it'd be possible to like use your mouse, or if you can draw on the screen or something like to that effect, and just help me identify which is aerosols, or the plot after this. Yeah, here.
Yeah.
Where are we looking at the boundary layer aerosols, and which ones are clouds, basically?
Yeah, of course.
Thanks.
So looking at just first in the normalized backscatter. So what you can identify as high ice clouds, especially with this volume depolarization ratio up here, and then these up here are all ice crystalline structures. And then down here, where it's obviously very bright white on both of these, can be identified as water clouds. It's much harder to see on the volume depolarization, but it is visually there because it has the drop in the volume depolarization along this line, which indicates water clouds because of its more unified structure of sphere. So the addition of the volume depolarization ratio makes this area here much clearer to read. So down here, it has very little change in comparison to what you'd assume is just like the background air, but with the volume depolarization ratio, a clear air, it's not exactly easy to see because of just how aerosol dense this is, but clear air would probably be this like blue over here. But all of this area here is aerosol that obviously had come in with these cloud layers. And so here is the high scattering, what I assume to be aerosol, due to it's just slightly too low to be what I'd assume is a crystalline structure.
Okay.
Yeah. If that's good.
Yeah, that's great. That helps.
I'm curious about the difference in your sites. Are you able to do these comparisons at any of your other sites?
So as of right now, this is the only one with like a solometer, but in Eureka, we do have several other LiDARs that are operating, and hopefully I'll get access to that data at some point, and I can do the comparison between what they're observing there. Obviously, it's going to be like slightly different because of the much higher functionality of some of the LiDARs up there, but it's eventually, hopefully.
Okay, and what about the urban sites, right? Like Toronto and Halifax. I assume those are going to be very different.
Yeah. So my assumption would be for Toronto that it'll be a little bit more aerosol deep with like the planetary boundary layer, but overall, the parameters of the algorithms shouldn't be affected by the urban pollution as much, just because of like the layer depth that we implement to say what is a cloud, like the parameterization of what we determine as cloud. And in Halifax, so our Halifax machine hasn't taken data yet, but it's not necessarily going to be an urban environment. It'll be a marine environment that it'll be observing, as it'll be a little bit outside of Halifax. So,
oh, interesting.
Yeah.
Where so I'm from Halifax. Where exactly is it going to be?
It should be south of Halifax, like 30 minutes south. I'm not sure. I forgot the name of the site, but it should be around there. It's like 45 minutes south.
Oh, interesting. Okay, thank you.
Coast, yeah. Okay.
Any other questions?
I just have a quick like reference kind of thing. Like if you're really trying to take a look at cloud-based, I'm wondering if there's any separate or like other source like radar kind of instrument can also, I'm more meteorology based, so maybe others can make sure your cloud top or like cloud base is confirmed as well, because like one of drawbacks of LiDAR is like only point observation, and you also need to think about like the errors embedded in the observation itself. So sometimes you can remove all the errors, but they can be real signals as well. So maybe that's one of good like supportive evidence to have the cloud top base, even though like I don't know, I have a bunch of experience in United States, so I'm not sure in Canada, but maybe that's one way to take a look at it.
Mm-hmm. I know that obviously there are several research sites around London that will give radar data. That would be very useful to determine their cloud base. But currently, due to sort of like the way that we're operating our co-located LiDARs, we're about like, we have just under like 15 meters distance between these instruments. So their observations should be within a margin of error, pretty much the same. But obviously, if we were to go much farther distance for the radar, it would have to include the modeling that would for the clouds to drift in, which would be a future addition.
Yep, yeah, I totally agree. Radar cannot be easy to move around. So
yeah,
I totally agree. Yeah, thanks.
Cool.
Okay, final check. Okay, I think that's good. So yeah, thanks, Victoria. Thanks to all the speakers for some great talks. So there is a poster session, starts at 11:45, CST, of course. I'm not sure, I don't think there's any specifically air quality focused posters, but please correct me if I'm wrong, but definitely some interesting topics otherwise. And then the air quality talks will continue after the poster session at 5 to 1 Saskatchewan time, I guess we'll call it. So yeah, I hope to see everybody back again. And yeah, again, thanks again to all the speakers.
I think we still have 6 more minutes if they have additional questions, until 11:35 CST. But like, if not, you can wrap it up and finish it. It depends on you. Yeah.
I think people are dropping. So yeah, it's great.
Yep, then I will just stop recording and finish the session here and see you in an hour or so.
Are you back again?
Yeah, I'm taking care of all the volunteering.
Excellent.
2020, 2020, 2030. Yep, all day. Yep.
That's great. Thanks for your help.
I will stop recording now.
Great.